All right, about to begin in like 20-30 seconds, probably. All right, got my notes. All right, welcome everyone. We got our new board here, so a little bit bigger than before. And we were discussing linear algebra. We're going through the abstract theory, but I kind of realized as I was going through today, we're going to finish on matrices. And so I'm going to kind of veer a little bit off from Axler, and we're going to talk about like determinant of a matrix, trace of a matrix, and yeah, there's certain properties that of a linear transformation that are sort of true in any basis, and these are a couple of those things. So determinant of a matrix, determinant of a transformation, and trace of a matrix, trace of a linear transformation. These are going to, in some sense, be defined differently, but in the end, they'll be equivalent to each other. So I looked online actually, and there's like 50 different ways of defining all of these things. Like, well, not trace mainly, but determinant. There's like product of all the eigenvalues up to multiplicity. There's this really long sign definition that involves permutations. I don't know, maybe some of you know some other ones. There's also like cofactor expansion. So yeah, there's all these different definitions of determinant. So Axler, he like kind of pushes all of this stuff to the end, which I think is maybe smart from a theoretical standpoint, but a lot of first year, second year linear algebra students in their undergrad, they're going to be a little bit confused why this is necessary. So I wanted to go a little bit into. I don't want to completely veer off from Axler, but I do want to talk about matrices a little bit for this week, and some of these other properties of matrices, properties of determinants, stuff like that. Is that tape? Yeah, it's not holding it up. It's just tape around it that kind of like seals the end. But this is like a gigantic sticker, basically. Like the whole back is adhesive. So yeah, it is tape, but it's not holding it up. It's basically one giant sticky sticker that's stuck to the wall. But yeah, um, I I'm a fan of the new board. I mean, you can't really move it easily, but other than that, it seems to be pretty great. Yeah, so this will be lesson 16. And then I won't have to erase as much, so that should be good for the coherence of the lesson and continuity and such. Also, a sticky board. Oh yeah, also it's magnetic too, so I can came with these magnets, so I can like stick stuff to it as well. So that's pretty cool. And I got this eraser. I know. I'm nerding out on all the unimportant stuff. So lesson 16, rank-nullity theorem. Just give it a little. Right. So last stream, I think it was Friday. Probably so the last lesson, or no, we did I think it was Friday. Um, we talked about the null space and the range of a linear transformation, right? So let me just remind you of those definitions. So let T be a map from V to W. Actually, I don't like this. Let me change the color. Right, so we're still talking about linear maps, right? So let T be a linear map from one vector space to another, from V to W, so just any two vector spaces. Usually they'll be finite dimensional for what we're talking about, but they could be any vector spaces. And then the null space and so the null space is all the vectors in the domain that map to 0 in W. So this is by definition it's all V in V such that T of V is 0. The 0 vector in W. I'm a nerd magnet, yeah. Right, and we proved last time that if we look at this set, that it was actually a subspace with all the same operations as V. So if I add two vectors in the null space, T of that sum is still 0. And yeah, if I multiply a vector by some scalar, then T of the vector was 0, so the scalar multiple is the scalar multiple times 0, and yeah. So we proved it was a subspace, closed under addition and closed under scalar multiplication. And then the other one we didn't really talk about too much was the range. And this was, so range T, this was just all the vectors in the codomain here where there's some vector here that maps to it. So maybe there's some vectors here that no vector maps to it, they wouldn't be in the range, but this is just all the vectors that have something that maps to them. So all the W in W such that there exists a V in V with T of V equal to W. Right, is the red too? No, you can read that, right? Yeah. Right, so a linear map between two vector spaces, right? Remember the vector spaces are always over some field, F. Then the null space is everything that maps to 0, and the range is just everything that gets mapped to something, or sorry, everything in the codomain where something maps to it. That would be probably a better way to say it. Okay, and we showed last time that both are subspaces. Right, but it's good to remember that they're subspaces of different spaces, right? The null space is a subspace of V, and the range is a subspace of W. So they don't even live in the same space. That's a common thing I think people mess up. They try to compare them in some way, like take the intersection of them, or something that doesn't necessarily make sense. Unless V is equal to W, right? You're mapping to the same space, you have an operator. And then in that case, you can talk about the null space intersecting with the range or something like that. But that's only if you're mapping to the same space. Yeah, there's no glare. I put up a light over here, but I think the angle I have right now is not leaving any glare, hopefully. Okay, so two subspaces of different spaces, one's a subspace of V, one's a subspace of W. Right, and then, so yeah, now we want to go into this main theorem. So they call it the fundamental theorem of linear algebra, or sometimes it's Rank-Nullity theorem. It has a lot of fancy names, but really the content of the theorem is pretty simple to understand. The proof is, maybe you have to be a little bit more careful, but just the statement of the theorem itself is very simple but very useful. And as the name suggests, it's one of the most useful theorems. It might be fundamental to the subject. So actually, let me get rid of. Let's do some blue now for some color. Hope everyone's having a good start to their week. Okay, so this is 3.21. I'm still in Axler, so we haven't gotten to matrices yet. I can't get this marker open. Okay, so this is 3.21. And actually, I'm going to split this into two different ways of thinking about it. So I'm going to go with the argument that's presented in Axler first. That'll be on the left. And this will be like my own sort of other way of thinking of it. So two different ways to think of the same idea. And the idea, so the thing that we're thinking about is this Rank-Nullity theorem. It says that the dimension of the codomain, so you have we're still talking about a linear transformation between two vector spaces, and now they're finite dimensional spaces. Well, really we just need V to be finite dimensional, but so the dimension of V, this finite number, is the sum of the dimensions of these two spaces, the null space and the range. So this is the dimension of null T plus the dimension of of the range of T. Okay, so this is the main statement. So basically, it's just comparing the size of the space of the domain, which is some integer, and it's splitting it. It says it splits as the sum of the dimensions of these two individual spaces, and this really restricts what types of linear maps are possible. For instance, later we'll in a couple seconds we'll show a couple things about injectivity and surjectivity between spaces. So the dimensions and the fact that the transformation is linear, like I said, really it forces certain properties basically. So these transformations can't act like wildly. Like you could imagine a discontinuous function can kind of do whatever it wants, right? And then a continuous function is more restrictive. So a linear function is like even more restrictive than that. And this is one of the restrictions that it forces, that the dimensions sort of have to add in this really restrictive way. Okay, so like it's not possible to have two different it's not possible to have, transformations where like these don't add up, basically. Okay, so actually I didn't really leave myself much room here, but I wanted to go through the argument a little bit. I could probably fit a little bit. So just to sketch Axler's argument here, so he chooses a basis for the null space first, because he proved previously that every vector space has a basis when we're dealing with finite dimensional stuff. So he first chooses a basis for the null space of T. Then he extends it to a basis for all of V. So start with null T, it's a subspace. You start with the basis, it's linearly independent, so we can always extend every linearly independent set to be a basis for the full space. So extend to a basis for V, then we have to add some number of vectors. So now we have a full basis, so it's U1 through UM, v1 through vn, right? Some large basis. Now the total dimension of V is of course m plus n, because we had m vectors that spanned the null space, and then we added n vectors, and this thing is still linearly independent, so the full dimension is just the size of any basis, so it's m plus n. Okay, and then the final step is he just shows that, so we already know that the dimension of the null space is m, and then we just have to show that the dimension of the range is n. So he shows that, the last step, he shows that if I take these vectors v1 through vn and I plug them into the transformation T, then T of v1, T of v2, and this new list is a basis for the range of T. So he shows that T v1, T v2, T vn is a basis for range T. Okay. Is everyone okay with this argument here? So we're showing that the dimension of V is the sum of the dimensions of the null space and the range, which is sometimes called the nullity of the transformation and the rank. So the rank is the dimension of the range, and the nullity is the dimension of the null space. So sometimes you'll see this theorem called the Rank-Nullity theorem, or in another sense you'll see it called the fundamental theorem of linear algebra. And when it's in that form, I would say it's more similar to like the fundamental theorem of group theory, where so I'll show in a second this other way of thinking about it. But in this other way of thinking, it's I would say it's more like an abstract algebra way of thinking of it, whereas this is more like a linear algebra way of thinking of it. So in the other way of thinking of it, in the fundamental theorem of linear algebra, there's actually an isomorphism between a certain quotient space. So you can take a quotient of a vector space, and that's also a vector space. So the other way of thinking of it is that we have V mod the null space, and this is isomorphic as vector spaces. So isomorphic meaning that they're the same as vector spaces up to just relabeling all the elements. So V mod the null space is isomorphic to the range. As F vector spaces. And then when you think about it in this second way, really this is actually saying more, this is actually more information than the Rank-Nullity theorem, because not only are we saying that these dimensions add up, as we'll see in a second here, but that these structures are actually the same vector space. So this quotient space and this range are isomorphic as vector spaces, and that means necessarily that they have the same dimension. Can anybody tell me what's the dimension of, so we did quotient, I did quotient groups in like lesson 2 or 3 or something a couple months ago. So we said if we have a homomorphism between two groups, we could form a, well, you don't even really need a homomorphism, but if I pick a, we needed it to be a normal subgroup in that case, but for vector spaces, every sub vector space is normal. Right, I'm using a lot of language here, but really what I'm trying to ask is, who can tell me what the dimension of this quotient space is? So we take V and we say all the vectors in the null space, those are now equivalent to 0, basically. So yeah, let me write down the question. So if this is true, then the question is, what is the dimension of this? And then what is the dimension? Well, this is just whatever it is. Right. So really, yeah, what is the dimension of this quotient space? That's the question we want to know. Offend them with the... Oh, wow, same time. Dimension of V minus the dimension of the null space. Yeah, that's correct. Yep. Yeah, so I'm not going to prove that, but you could imagine why that's true, right? Because in the quotient space, everything in the null space is equivalent to 0. So yeah, it's sort of like we can write every vector as some linear combination of vectors in the null space. Actually, the arguments are very similar. Like you would start with the basis for the null space. All of those vectors are now 0 in the quotient space. So you could kind of throw all of those vectors out of the list and you get a minus dimension here. So really it's the dimension of V minus the dimension of the null space is equal to the dimension of the range. And if you rearrange the minus into a plus, then you just get this rank-nullity theorem statement back. So it would just be dimension of V minus dimension of the null space is equal to this dimension of the range. Okay, so I just wanted to give you kind of like both perspectives, because if you're studying group theory, you would sort of think of this statement in this way as a statement about the quotients, that the V mod the kernel in some sense is isomorphic to the image, would be the group theory statement. Matt, look at 3.99, page 99. Could you sum it up for me? It's kind of hard for me to look at it while I'm, well, I guess I could look at it for a second. So page 99, 3.99. All right, I'm looking it up in the book. 3.99. Okay. Oh, right. Quotient space. Yeah. Right. I didn't really want to go over it too much because I didn't want to waste time on it. But yeah. Rex is pointing out that the definition of quotient space is in 3.99 in Axler. So page 99, 3.99. If you're curious, that's where he defines quotient space, and he'll tell you what the, how do you add two vectors in the quotient space? How do you scale by some vector, how do you scale by some element of the field? Right, but it's the same definition as for groups. So in fact, this definition is actually easier because we're dealing with an abelian group structure. So like I was saying, every subgroup for an abelian group is automatically normal because everything commutes, so there's no non-commutativity issues. So yeah, if you are curious, Rex is pointing out that 3.99 tells you how to form quotient vector spaces, and I believe somewhere around there as well probably talks about the dimension. So it'll say the dimension of the quotient is the dimension of the full space minus the dimension of the subspace that you're quotienting out by. Okay, so I think that's good for right now. So two different ways of thinking about this fundamental theorem, but the statement itself doesn't change no matter how you want to think of it. I'm sure there's probably other ways of thinking of it as well. The statement, though, is just that the dimensions add, that the dimension of the null space and the dimension of the range add up to be the dimension of the domain. Okay. Any questions? So that was 3.21, Axler. Last chance before I erase. takes a little longer to erase though. That's not that that's that big of an issue. Okay. And so I'm gonna, I'll skip around in a little bit, but actually I'm not skipping around here. So this is 3.22. And we're gonna do 3.24 as well. So very similar statements here. This is what I was talking about with the Rank-Nullity theorem. It forces certain things to be true about linear transformations. So one of them is that if you have a linear map between two spaces, so let me write it out to be perfectly clear. So if I have a map between V and W and it's linear, and we have that the dimension of the domain is larger than the dimension of the codomain. So this space is bigger than this space that we're mapping to. Then that automatically means that T is not injective. Okay, and if the dimension of V is less than the dimension of W, then there's no way for T to be surjective. So the other way. So T is not surjective. All right, so why is this the case? Well, it's just a simple counting argument with the dimensions. So here in the first case, the dimension of V has to be equal to the sum of the dimension of the null space plus the dimension of the range. But the dimension of the range, it's a subspace of W, so the dimension of the range has to be smaller than the dimension of W. Right, so let's just translate what that means. Let me write in a different color. Right, so for this first case, so this is equal to the dimension of the null space plus the dimension of the range. But this range is a subspace of W, so in particular, it must have smaller dimension. Yes, new whiteboard. Wait, so I lost my thought here for a second. Hold on. So we're trying to show that T is not injective. So the reason that T is not injective is essentially because this null space must be non-trivial. So if the null space is non-trivial, that means it's sending, well, it sends 0 to 0, but it also sends something non-zero to 0. And that means, you have two different things going to the same thing. That means the function's not injective, right? So basically, this space is bigger than, the dimension of V is always larger than the dimension of the range because the range is a subspace of W, and you have inequality that way. Right, so what am I trying to write here? So this is smaller than, yeah. So basically, yeah, so this has to be non-trivial, yeah. So dimension of the null space is greater than 0. Right, because there's no way these two things can add up to be a number that's larger unless this thing is at least 1. right? 1 or larger, because this thing has to be less than this. Yeah. So that forces this number to be bigger than 1. Or, it could be equal to 1, but it has to be larger than or equal to 1. Right? And if the dimension of the null space is greater than 0, that means that there exists some non-zero vector v not equal to 0 such that t of v is 0. Right? But linear transformations also send 0 to 0. So if something non-zero goes to 0 and 0 goes to 0, that means not injective. Okay, so and then surjectivity is similar. You just make the argument the other way. Right, yeah. So then dimension of v is less than this thing. So then, yeah, basically you just have to show that the dimension of range t is smaller than the dimension of w in the other way. So actually, it's not exactly the same argument, I think, but it's not very difficult. It's another simple argument about integers, basically the sizes of integers. Any questions? I will rank your nullity, yes. Right, so just the fact that t is linear, you're dealing with finite dimensional stuff here. Based on the dimensions of the domain in the codomain, you can automatically say something about the injectivity or the surjectivity of the function, depending on, if you have this mismatch one way or the other. And that's important, right? Because a lot of, important math things that we study depend on whether a map is injective or not injective. You talk about embedding certain spaces in other spaces, right? You need injective maps only. So injectivity is a common thing we study in math, and yeah, you have some rigidity in the properties in the case that it's linear that we're dealing with here. So, okay. So certain things say t is not injective. Other property says t is not surjective, right? Okay, yeah, I think that's it for now. So I'm going to go to section 3c in Axler. So now we're going to start dealing with matrices. So yeah, this was basically, there's a lot of stuff you can read in Axler. I don't have time to go over like every little detail, of course. But yeah, now we're going to start going into matrices. So sometimes in linear algebra classes, they just go right into matrices immediately. I kind of like that Axler first deals with the abstract stuff, talks about a basis first, and then once you deal with the notion of a basis, then you can talk about the linear transformations. Once you fix a basis, then you can talk about matrices. So yeah, I think we've kind of talked about everything we need to deal with. So now we're going to talk about if we have a linear transformation and we fix a basis in the domain and the codomain, how do we form this matrix? What's the definition, and what's the importance of the definition of the matrix of the linear transformation? Yeah, sorry about the ads. I turned on the ads, but I did not touch the settings. So whatever the default settings are, it might just run ads in the middle of this. I apologize if it does. I'll have to fix the ads. I probably won't run ads in the lessons, but I might run ads like at the very end or something. Or if it's like a long like research type thing where I'm talking for like 2 or 3 hours, I might start it after like a couple hours. But yeah, I don't want to run ads in the middle of this stuff. But yeah, if you do miss something, it will be on YouTube later. So type ! YouTube. You can get the link to my YouTube, and so then you won't miss anything there. But yeah. Okay, so that was Rank-Nullity. Now we're going to go to 3c in Axler still. But now we're going to start with Axler with matrices, but in section 3c, but then we're going to sort of tomorrow, actually, yeah, starting tomorrow on Wednesday, I'm going to start doing exercises dealing with matrices, but we're going to follow other sources. So I put a couple sources in the resources section on Discord, which is like There's one called Linear Algebra Done Wrong, which is kind of like the opposite of this book, where he just jumps right into matrices immediately and starts dealing with calculations. And then there's another one by Anton, I think, that Pensetter suggested. And I looked through that one real quick, and that looked like kind of like a standard. They deal with the cofactor expansion definition, so that's another good source. And yeah, so now we're going to be dealing with matrices, and we'll probably be doing that for the rest of the week, including Friday. But Wednesday, I'm going to go over a lot of exercises, so you'll see. I want you guys to see, if you're watching this and you're a student of linear algebra or a new student to linear algebra, I want you to see how to do these calculations by hand, so that now if you've watched all these videos, you've seen the theoretical side, and now we're going to deal with the more computational side of writing down the matrix of a linear transformation, calculating the determinant. You might have to calculate reduced row echelon forms of a matrix. So yeah, different stuff like that. So now we're going to kind of marry the two ideas where we dealt with the theoretical side. Now you have the computational side, and hopefully, it makes the computation make more sense, hopefully. Squeaky, squeaky. Okay, so this is section 3C, Axler still. And this is 3.31. Right, so 3.31, the thing I'm about to write, I'm not sure if this is a definition. Yeah, I guess it's a definition. So it says, given a linear map between two vector spaces, let's assume they're finite dimensional. So let T be a map from V to W, be linear. And what we need for this definition is we need a basis for the domain and a basis for the codomain. So a basis for V and a basis for W. And let's just call them beta 1 and beta 2. So beta 1 is a basis for V. And W1 through Wm is a basis for W. So be bases for V and W respectively. So then the definition is then we can write down a matrix, which is basically this 2x2 grid of coefficients. In other words, they're elements of the field F. And the matrix, in some sense, is going to store all of the important information about the linear transformation, in the sense that if we know what the two bases are, then we can recover the linear map just using the information in the matrix. So in some sense, it's really storing all of the important information about the transformation. So it says the definition is that the matrix of the transformation T with respect to these two bases maybe I should, hold on, it's a bad spot for this. So then it's a I think I said 2x2 before, but I mean n by n grid, or sorry, n by m, depending on, actually it's m by n. So it's the dimension of the codomain times the dimension of the domain. And what you're going to do is you're going to take in each individual vector from the domain, which is v, and you're going to send it through the transformation, and then you're going to write the coordinates down of that vector with respect to the basis in the codomain. So basically we take t of v1 we write it as a coordinate vector. So meaning we take v1, we send it through the transformation, and then we write it as a linear combination of the vectors in v2. And whatever those coefficients are, they're coefficients in f, those coefficients go in the order as this first column. Then we do the same thing for v2. We send it through the transformation. We look at the coordinates of the linear transformation, of the linear combination of the wi's that give you t of v2, do t of v3, and so on. So each column is going to be t of vi written as a coordinate vector with respect to this beta 2 basis. And we're going to do that for each column. Okay, so kind of a little bit of a doozy of a definition, but there is definitely a method to the madness. There's a reason for the odd seeming definition. But I guess the important part, like I was saying before, is that if you know what the two bases are and they're fixed, and you know what the matrix of the linear transformation here is, then you can actually recover how the transformation acts on any vector in V. Since every vector in V is some linear combination of these VI's, and we know where the VI's get sent based on the coordinate vectors in the matrix, then if I pick any other vector, then because of the linearity, you can actually recover the coordinates of that new vector that you, because we actually only know where v1 through vn goes, but the fact is that because it's linear, we can actually extend by linearity and take any linear combination of these vectors, and we also know where that gets sent by t. Okay, so are there any questions? Got a couple comments. Why am I getting window cleaning ads? Right. Yeah, there's the YouTube. Right, so this definition just depends on, you have a linear transformation between two vector spaces. You fix two bases for those two vector spaces. Then once the bases are fixed, there's a unique matrix for that linear transformation. But it depends on the basis sometimes. Of course, if you have a linear transformation like the zero transformation where you send everything to zero, then no matter what bases you pick, the matrix is always going to be all zeros, of course. So that's kind of like a special case. Yeah, but most of the time the matrix depends on the two bases. So if you change, there's actually a change of basis formula where if you change the basis, you have to conjugate by a certain matrix, change a basis matrix, and then you might get a new matrix. But that's only for certain transformations, right? Most transformations actually, but some transformations will be like somehow invariant where their matrix is essentially the same in any basis, but those are like special cases. Like some of them are the identity matrix, the zero matrix, right? If you conjugate these by anything, you get the same thing back. All right, any questions so far? So this is basically just a definition. It says we have a linear transformation, fixed bases, you get this matrix, and it gives us important information about the transformation. Right, so I wrote down this next section, but I think I might go over this a little bit differently than I had thought of. Right, so what is the point of this definition? I guess if you've taken linear algebra before, you know that if you have two matrices, you can multiply them together, and there's a notion of multiplication of matrices. But it's not exactly obvious that with that definition that the multiplication actually, like, what does it correspond to? But so I want to make it clear here that when we multiply matrices, what we're actually doing is we're keeping track of, in some sense, we're keeping track of the matrix of the composition of the maps. So there's, if we have a matrix for two different maps and we compose the linear transformations and we keep track of all the bases, then the matrix for the composition corresponds to matrix multiplication. So it's in some sense, the matrix multiplication is matching up with how we compose these linear maps and keep track of all the coordinates with all these different bases going on. So yeah, I said a lot of things there without writing it down, so it's pretty hand wavy, but the thing that I want to make clear, I'll write it down here. So without actually explicitly writing down what the definition is for matrix multiplication, I still want to give you this important idea, which is that, so if I have a linear transformation T from V to W, and I have another linear transformation from W to some other vector space, let's say R, are both linear, then, so the idea is we can compose these two linear maps, we get a new linear map, but what is the matrix of the composition in terms of the matrices of the individual T and S? And that's where your multiplication of matrices comes into play. So it says, if I pick a basis for V, W, and R, so let's say that we have a basis beta 1 for V, beta 2 for W, and beta 3 for R. Then the matrix of the composition, S composed with T, in the basis of beta 1, beta 3, is the product of the two matrices S, beta 2, beta 3, times the matrix for T, beta 1, beta 2. Okay, and this right here is this matrix multiplication, which I haven't defined. Maybe I'll give it an exclamation mark. Okay, so this statement is pretty important for linear algebra. It says, when I compose linear maps, I get another linear map, and this is in some sense like a product on this space of linear maps. And when I translate things over into matrices using these bases for V, W, and R, then the matrix of the composition becomes an actual product of the matrices if I keep track of, which bases I'm writing down these matrices with. But as long as I write down T, the matrix of T with respect to the basis for V and W, and I write down S with respect to the basis for W and R here, because S is a map from W to R, then if I take these two matrices and multiply them using this notion of matrix multiplication, well, then I get the actual matrix for the composition of the two maps, as long as I'm looking at the bases beta 1 here and beta 3. So the basis for V and the basis for R. Okay. So yeah, I think I'm not even going to really waste time writing down the definition of matrix multiplication, but you really should know that when you're doing matrix multiplication, this is actually what you're doing. You're keeping track of the coordinates that make up the matrix for the composition of the two maps that are represented by those two matrices. Okay, so any questions about this? So far we talked about rank-nullity theorem. We talked about the matrix of a linear transformation once we fix a basis for the domain and the codomain. And then we said that now we're talking about the matrix of the composition of two linear maps and how it relates to the matrices of the individual maps. And that relation is that compositions become products of matrices. Okay. So no more questions. Yeah, let's just do an example real quick of a product of two matrices. Actually, I don't really want to go into the definition. So probably let's save that for Wednesday probably. Yeah, just because I don't want to write down, like, it's not a hard definition, but it's a tedious definition to multiply two matrices. And then I'm just going to end up writing a bunch of stuff and probably confusing whoever's listening anyway. So yeah, I think this idea is actually probably more important than the actual, like, computational definition itself. Like, because you can always write down any computational definition, but if you don't understand, like, what's the point of it, right? So the point here is that you're actually, matrix multiplication is actually doing the work for you of computing the matrix of the composition of the two linear maps. Okay, so yeah, we'll go into computational. I'll go into a little bit more computational stuff probably tomorrow on Wednesday when we do the exercises. Right, yeah. And then this last part, I guess I wanted to go through one example where the rank-nullity theorem is sort of illustrated here for some abstract vector space. Yeah, and then we'll just do more exercises tomorrow. Well, this isn't even really... Yeah, I guess it's an exercise. Excuse me. Okay, so I just came up with a linear transformation between two vector spaces, and then we wanted to write down the matrix, or we want to see an example of how to write down the matrix. So for this example, well, I sort of made this up, but the idea is in Axeler, of course. So you have polynomials form a vector space over a field. And in the book, he writes this as P3 of R. This is all polynomials of degree 3 or less. And I'm going to make a map to itself. And this map is going to be differentiation. So we're going to take a polynomial, and we're going to send it to P prime of X. And this is linear. So for example, x squared gets sent to 2x. Right? So now what we want to do is basically, since we know that this transformation is linear, we want to glean more information out of the transformation. One way to do that is to just fix a basis and write down the matrix, and then you can actually figure out what the rank and the nullity of the transformation is explicitly from the matrix, in fact. So in this case, so what is what is the matrix of T? And let's just say it's with respect, so the domain and the codomain are the same here. We're going to use the same basis here, and the basis I'm going to use is this. We could call it the standard basis for polynomials. It's just 1, then x squared, and then x cubed, and then we're only going up to degree 3, so that's all we need. So it's a 4-dimensional space. There's a basis of 4 vectors. I just listed them. What is the matrix of this linear transformation where we take the derivative with respect to that standard basis I was just saying, 1x, x squared, x cubed? So that's the question. So it's going to be a 4x4 matrix because the domain and the codomain are both dimension 4. And so what's the first column of the matrix? Anybody that's paying attention right now? So we're going to take basically the first vector in the list for our basis in the domain, map it through the transformation, so we're going to apply the derivative, and then we're going to write that new polynomial that we get in the coordinates of that same basis. So some linear combination of 1x, x squared, and x cubed. Yeah, so the derivative of the first basis vector, so the first polynomial is in the list for the basis is 1. We take the derivative of 1, and then Effendum says that the derivative is 0. That's correct. Yeah, derivative of any constant is 0. So the polynomial is 0, but the coefficients of the 0 polynomial are 0 times 1 plus 0 times x plus 0 times x squared plus 0 times x cubed. So it's 0 plus 0 plus 0 plus 0 times the last one. So that gives us the first column. And then, yeah, we do something very similar. So we take the next basis element in the list. So that would be, so we started with 1. Now we move to the next one. It's x. We take the derivative of x. We get 1. And then we write 1 as a linear combination of those polynomials. So it's 1 times 1 plus 0 times x plus 0 times x squared plus 0 times x cubed. Let me just write down the basis here just so we're not fully confused. So this is 1x, x squared, x cubed. This is our basis. Right, then we go to the next basis element, x squared. And we take the derivative of x squared, so we get 2x. 2x is 0 times 1 plus 2 times x plus 0 times x squared plus 0 times x cubed. And then finally we take the last element in the list, x cubed, and we take the derivative, we get 3x squared, so it's 0 times 1 plus 0 times x plus 3 times x squared plus 0 times x cubed. Does it not have to be ordered? Yeah, it has to be ordered. Yeah, I wrote it as a set, but yeah, technically it does have to be ordered. That's a good point. And when we're talking about these lists, they're technically not even sets because they can repeat. But if you ever have a list that has a repeated vector, then it's automatically not linearly independent. So you can kind of throw out the extra vectors. If your goal is to get a linearly independent list, you can always throw out the repeated ones. Yeah, so Effendum had a good question. Does it not have to be an ordered / a tuple? Yeah, it does actually, yeah. So the ordering matters. Right, if you change the ordering, what's going to happen to the matrix, in fact? If you change the ordering of your basis elements, the columns are actually going to switch. So in that sense, you can see that the order definitely matters. It's going to change the matrix immediately. Assuming not all the columns are the same, right? Okay. Any other questions here? So we had a linear transformation between a vector space to itself. We had a basis which was then a basis for both the domain and the codomain, since they were the same. The linear transformation was take the derivative, you get a new polynomial, and we plugged in each polynomial from the basis. We took the derivative and we rewrote the derivative as a linear combination of those basis elements. Right, and then we got this 4x4 matrix. So this 4x4 matrix, these 16 numbers actually tell you everything you need to know about differentiating a polynomial. In fact, if we take any other polynomial, it's a linear combination of these. And because differentiation is linear and I know how to take the derivative of these, I can take the derivative of any polynomial just by writing it as a linear combination of these and then taking the derivative individually, separately using this matrix. And then I just can add up the result. Add up the linear combination of the results, actually. Okay, so yeah, we'll do some more problems with matrices. We'll talk about determinant and trace on Wednesday. And we'll do some examples of calculations, and we'll talk about how these determinant and trace quantities actually don't depend on a basis. So they're, in some sense, they're coordinate independent, meaning that so there's certain properties where, if you fix a basis first, and then you calculate something that's dependent on that basis, and it might change depending on which basis I pick, then that's not really a coordinate-free invariant, right? Because I had to pick that particular basis, and if I picked a different basis, I might get a different number, right? So in linear algebra, one thing that's important to study is we have this linear transformation. It might be nice to be able to sum up some information about that transformation just based on like one number or two numbers or whatever it is. Right. Or whether the transformation is invertible or not, right? So the determinant will actually tell you if the transformation is invertible or not based on whether the determinant is 0 or non-zero. So stuff like that. And then it turns out that the determinant actually doesn't depend on a choice of a basis. So you can actually fix a basis, get a matrix, and then calculate the determinant from the matrix. But it turns out if you pick a different basis and you get a different matrix, you actually get the same answer in the end. So that's actually one of the amazing or interesting results in linear algebra, that when you calculate the determinant of a matrix, it doesn't depend on what basis you chose. You get the same answer. So yeah, we'll get more into this on Wednesday, but yeah. So let's read n simplex. Is that the spelling there so I don't get it wrong? But yeah, is there any... Let me stay here for like another minute while we clear out of here, but is there any other questions about this stuff? So we're talking about basis here, rank nullity. Fixing a basis, you get matrices. Yeah, and we'll continue from there. Let me see.